All right, the last topic I want to talk about in today's lesson is Snell's law. And Snell's law is an equation that you will find in your reference table, same place that we've been finding all these equations. And Snell's law is a way to relate the indexes of refraction of a beam that refracts across the boundary to the angles of incidence and the angle of refraction. So you can see here this equation is n1 sine theta 1 is equal to n2 sine theta 2. And the thetas are the angles measured from the normal, and the n1 and the n2 are the indexes of refraction for the different mediums. Now, they don't give it as incident and refractus by subscripts. They give it as ones and twos because when you talk about Snell's law, each one of these refractions is reversible, meaning that if you push a beam across the boundary and then you reverse the beam back across the boundary, it would follow the same path. So as far as looking at Snell's law, we don't identify indexes of incidence or refraction because both processes can be looked at either forwards or backwards. Let's go ahead and take a look at this problem, and we're going to look at an example of this. So this example in your notes for Snell's law says that a ray of light with a frequency of 5.09 times 10 to the 14 hertz is traveling in water. It has an angle of incidence of 35 degrees on a water-air interface. At the interface, part of the ray is reflected and part of the ray is refracted. As it enters the air, calculate the angle of refraction that the ray of light has. So we're dealing with water and air, and if you look at our index of refraction, indexes of refraction, you can see that air has an index of refraction of 1, and water has an index of refraction of 1.33. We can also see from the diagram and given in the problem that the angle of incidence at the water-air boundary as the light ray is traveling through water is 35 degrees. So looking at Snell's law, we have three of the four. We have our index of refraction for water, we have our angle of incidence for water, we have our index of refraction for air, and we're looking for the angle in air, and that would be the angle of refraction. So we have these parts. Let's go ahead and solve this and use the equation. So we're going to use the equation, Snell's law, n1 sine theta 1, n2 is equal to n2 sine theta 2, and we have to identify which medium is going to have each one of these ones or twos. So I'm going to take air to be the one subscripts, and everything in air will have a one subscript, and I'm going to take water to have the two subscripts. So n1 is going to be the index of refraction for air, n2 is going to be the index of refraction for water. Theta 1 is going to be the angle measured from the normal in air, and theta 2 is going to be the angle measured from the normal in water. So we have to first always make sure that we identify which of the two mediums is going to be the one, which of the two is going to be the two. And we've done that here. So doing that, we can start filling in the information we have from the problem. For n1, index of refraction for air, that's 1.0. Theta 1 is what we're trying to solve for. N2, which is the index of refraction of water, that's 1.33. And we have theta 2, that's the angle of incidence in water as it before it crosses over into air, and that's going to be 35 degrees. Solving this, our sine theta 1 is what we're trying to solve for, and then if you take the sine 35 and multiply it by 1.33, you end up getting 0.763. Now this is not the end of it. We have not found the angle, we just found what sine theta, or sine of the angle, is equal to. Now we need to isolate the angle itself, so we have to take the inverse function of sine, and we can figure out that theta 1 is going to be equal to the inverse sine of 0.763. So as soon as you get that sine theta equal to some number, you have to take the inverse function of that number to isolate theta itself. And when you take the inverse of 0.763, you find an angle of 49.7 degrees. So the angle as it refracts is going to be 49.7, and you can see measured from the normal, 49.7, it speeds up, it's bending away from the normal, and this is how we use Snell's law. Snell's law is how we determine the angles involved here, because the ratios and the index of refraction don't deal with these angles, but Snell's law does. Now you have one more example on Snell's law. Go ahead and try that. And when you're set with that, there's a CAS learning assignment that's on that last slide. Go ahead and do that and answer the questions within the assignment itself, and you should be all set for our refraction talks next week.